Yeah, so first I would like to thank also the organizers for the invitation to this interesting interdisciplinary conference. And before I start, some words to my title. So you will not now hear a classical type of biomarker talk where I show you spectra around M-star, Earth-type planets, infrared spectra or so. You will also not hear a talk on habitability of Earth-type planets around M-stars. The point is that I will connect more or less with this on the first two talks in the morning. So starting with Earth-type planets after their origin, so when they also outgassed or formed their early atmospheres, because also from the introduction and many other talks, if you speak about the origin of life, early life, most of you, when you take the Earth, you focus on the time spans when the earliest life forms on Earth evolved, and this was about 3.5, 3.8 billion years ago, but what was before? So the focus of the talk is to understand, to try to understand, and you will see it's very difficult from the atmospheric point of view how, for instance, a planet like the Earth evolved during these first 500 or billion years, so that the conditions, the right conditions are set on the planet. And this is, of course, also a crucial subject for exosolar planets, because we are interested to know if there are more planets outside in the universe which evolved similar like the Earth. And the second point on the M-star issue is that I show you some recent studies and ideas how we can use the discovery of, we may discover, we have some, but we may discover in the near future, next years, maybe tomorrow, Earth-sized planets inside habitable zones around M-stars, and how we may use M-stars to test atmosphere evolution scenarios, which are also relevant for the evolution of the Earth. So this is an overview, which it's a figure which was published in a review which I made with several colleagues. Some of them are also here on this conference, where we didn't study really, I mean, the conditions of the habitability, because this is a very wide range. So Mars may be habitable for some microorganisms. So or Titan or these icy satellites, what we did is we classified somehow habitats. And of course, one habitat, which we said it's a kind of class 1 habitat, is an Earth-type planet. It doesn't mean it's an analog. It could be larger or smaller if there are no restriction to the evolution of an environment like on Earth. So it should be a planet where you have, for a billion years, water, in that case liquid. You should have some continents, and you should have an atmosphere, so that life as we know it, at least here on Earth, could evolve, and also on the surface, so that the planet could also produce a biosphere, which may be studied in the future by spectroscopic observations from spacecraft or space telescopes. And of course, there may be planets evolving, which we said they are kind of class 2 habitats. This could be Martian-type worlds. Also, they may have started like our Earth, but they ended up even in the habitable zone, in the good condition, but they ended up not like Earth due to different conditions, maybe astrophysical, maybe host star type, maybe geophysical ones. Of course, maybe life evolved there, but it may stay on a level on microbial form. So if you know, when you research life on Mars, we have even to go there with rovers, and it's very difficult to find biosignatures, biomarkers, and so on. So in my talk, I will focus on this one, of course, to understand how planets may evolve during the early stage after the formation, so that we end up with an Earth-type body. And because with space telescopes, if it's very difficult to find life or traces of life on Mars, we may have never a chance to find the same biomarkers, let's say, on an extrasolar planet. And I will also not touch this subsurface ocean type habitats. There are talks in these sessions, I think, on it. And we have maybe exotic icy water world type bodies like LISA 1214b, maybe also habitats, but very difficult to, so they're different for sure than Earth-type planets, terrestrial type planets. And so what is the problem? Or there are huge uncertainties, not so many research groups around the globe studied this really so far. And we had also not much data on that, and there's a lot of speculation and of course models, and they give different results. But when I connect to the formation of the planets in this time, 4.5 or 4.5 billion years ago, so we had the young planet, but the evolution of the atmosphere or the environment of the planet cannot be seen separately from the evolution of the star, or in our case of the sun. And there are now a lot, really many astrophysical data since the past 10, 15 years, but the past years there are more and more coming in, which showed that the, let's say, X-ray activity, the EUV activity, short X-ray activity was much, much higher in this young stage of our sun, or also on other stars in that case, than at present. And this has a big impact in the atmosphere, and that I will come back later. Then also it's a huge uncertainty how the outflow of the plasma of the young sun or young stars really behaves. Is the outflow, we know that they lose a lot of mass, but it's not clear if this mass is lost over the polar areas or in the equatorial regions where you may have planets. But this has another tremendous impact. So if you have, of course, a dense plasma outflow, it affects the atmosphere and its evolution also. So then there's a question on magnetic fields. You may have intrinsic magnetic fields, that means a dynamo. We know in our solar system, if we take a look to the terrestrial planets, only the Earth has really a strong intrinsic magnetic field. The question is, what is the role in protecting an atmosphere for escape on that? Or you may even have induced magnetic fields in the upper atmosphere due currents of high ionized atmospheric constituents, you can say, or portions, which you can expect if you have very high X-ray UV fluxes. You will have huge ionization also ongoing. And then you induce magnetic fields which may also protect somehow the atmospheres. Then, of course, there is big uncertainties, and observations, and that would be nice to have. And this is what I address in the second part of the talk. So there is a lot of evidence that the very early atmospheres, so really after the origin of the planets, probably were very hydrogen-rich in the top of the atmospheres. There may be even water-rich steam-type atmospheres, like we expect on early Venus, shortly after the magma ocean period. There may be also an outgassing event in that time on a lot of CO2. The question is, how long does this atmosphere remain? What is the role in protecting it, or what happens if you don't get rid of it? Then it depends also on the availability of infrared cooling species like methane as an example, but this is easily dissociated in these very early conditions. CO2, of course, also is a good infrared cooler. And the question is also nitrogen-rich atmospheres. So if you say, well, we have our first traces of life 3.5, 3.8 billion years ago. Maybe the Earth had also a nitrogen-rich atmosphere, let's say 4.3 billion years ago. The question is, would this atmosphere be stable, or would it be gone, escaping to space? So all these issues are somehow crucial. And this slide more or less connects also to the first two presentations, but it summarizes a little bit what is the knowledge, or let's say kind of belief system in that way, how the atmospheres of terrestrial type planets may evolve. Of course, you have seen simulations by Alessandro Morbidelli, and some simulations by Raymond. and others. So that means, okay, you form your planet, and the next point, so that depends also on the initial water inventory of this planetary system, nebula, and also the planetesimals, and we should not forget the position of the giant planets, which may influence this delivery. So, but you can expect there is a lot of also water there in the early stage. And when you take after these planets accretiated, and if you make a review in many of these studies on the magma ocean, then you will soon realize that scientists who are studying this very early stage after the planet formation, that in this period, a huge amount of water which was in this material cannot be integrated into the minerals, and also CO2 in that case. So you have fraction of this which is possible to integrate in the minerals, but up to, it depends on the initial water inventory of this nebula also, several, up to 100 bar, up to 1,000 bars, even 10,000 bars, water vapor could be outgassed catastrophically according to these studies. So there are several, so if you take a review on it, you will come across this. And that means that, of course, some people focus then on our solar system, and you can expect that you may have also very early outgassed 400, 500 bars on water vapor, also 80 bars, something like that, on CO2. And this is really in a very, very early stage. And then you have, of course, also comets, we have these bombardments, we have the late heavy bombardment, which is anyway in a time where is earliest gassing and so on. People think, yes, the young sun was very active and the water gets rid of easy in that way. But there are not really so now, let's say, newer studies on that, because during the last 5 years, or even, let's say, 10 to 5 years, much more is known now on this early atmosphere response to high UV radiation. And it seems it's not so easy to remove, for instance, from planets with this mass and size like the Earth, hundreds of bars of water vapor, or CO2 in some sense also. So this shows you a summary of data, astrophysical data from different wavelength ranges, from sun-type stars. This is from the Sun in Time project. Of course, the general G star is not really parallel or an analog of these stars. So there's also a range. You may have G stars where the UV flux was not 80 times stronger in the early stage, but maybe 120, or you may have some with 60. So, but anyway, you see that the short wavelength radiation was very strong, much higher, normalized to the present value, which should be 1 in that case, during the first 700 million years. And this here is shows you the average, in that case, soft X-ray, which is close to the UV flux, normalized to the solar value of a wide range of G stars, F stars, K stars, M stars, and also normalized to the habitable zone distance of that. In that case, of course, with M stars, it's you have a wide range of masses, but this is a kind of 0.4 mass M star habitable zone in that case. So what you see is that G stars start more or less close to 100. When I say start, that means this is the time when the sun arrived at the 0H main sequence. And at that time that the Earth, for instance, or other terrestrial planets were formed. Then F stars are a little bit weaker, K stars a little bit higher, but it's kind of like this is maybe the lower part of the G and the upper part of G. And M stars, as you may know, are very active, and they also remain active over long time periods. So this should have an impact to the atmosphere evolution, of course. So what are the impacts? And we can test at least some behavior or response of the atmosphere, because we can take an analogy with our sun. When we have extreme solar events, that means really extreme flare events which affect the upper atmosphere. Then we have satellite data there, and we can study the response. What is the expansion of the present time Earth atmosphere under such a flare event, for instance? So this is done. It's also space weather. It has an impact, of course, on satellites. Some of them may even fall down, but you can use this data also and analyze it. So that means, for instance, a flare during the Halloween event. There are some studies on this published now, correspond to the average UV flux of the young sun when it was about 2.5 billion years old. And the impact was that the atmosphere, of course, was heated, started to expand to a much higher level than it is now. And so you can use some model validation on that. But of course, for the really extreme situations, it's not so simple. You have only data from the stars, but no atmosphere response for a 50 UV flux, for instance. And the model may give you a result, but we don't really know if we oversee something in that. So this is a point where we can test it, I think, in the near future, which I will address soon, by using observations of Earth-type planets around M-type stars, which are quite active in some sense, so they can be used as a proxy for the young sun also in a way. And what happens, of course, is, this radiation comes to the upper atmosphere, it dissociates gas, it ionizes gas, depending on the compositions. If there are some molecules which may irradiate part of this incoming radiation back to space, then you can have a cooling effect. Generally, if this is not the case, you heat the atmosphere starts to warm up, it may expand, and in the extreme case, this was more or less quite good studied by Dian Feng and Jim Casting and others recently, around 2008, where they showed that these atmospheres may switch to a mode from a hydrostatic, as we know it at present time, to a non-hydrostatic situation. And because these are now a summary from the literature of various studies from starting in the early 80s with Watson. There were also a Japanese group at the same time who did these studies. Also Jim Casting studied this behavior, also addressing the issue of the evaporation of the ocean on early Venus. You see, this is only a 5 UV flux, 5 times higher UV flux, which is nothing to the really young sun period. But in that case, if you have a hydrogen-rich upper atmosphere on an Earth mass and size planet, the exophase, which separates the collision-dominated from the non-collision or less collisionless regime, moves up to 7 Earth radii. In the case of the Earth, for a nitrogen-type atmosphere without an additional amount of hydrogen, we end up with these cases where you see that when the UV flux reaches 20 UV, you have even an exophase above the magnetopoles. So the atmosphere starts to expand. The magnetic field in that case doesn't protect it anymore, and the solar wind or stellar wind in the case of a star can ionize it by charge exchange and remove it. So this here, now I come to the last slides, where I try to show you some, present you some preliminary new studies where we may find out if this is if this happens really in this early stage of the atmospheres. So this picture here is present Earth, an observation by NASA's Interstellar Boundary Explorer spacecraft, which observed so-called energetic neutral atoms around the Earth's magnetopause. So this is the Earth's magnetopause, and that means that some neutral particles from the exosphere reached the magnetopause level, even at present Earth, and solar wind protons can interact with them by charge exchange, and the particles you see here are not Earth's exospheric particles, but they are energetic neutral atoms from the solar wind in our case. So what happens in this, you can imagine this is the present Earth. So if you would have a very strong magnetic field or protection or a very compressed atmosphere, because maybe it's a super Earth with a very dense planet, then if no neutral particles reach this, overcome this obstacle, you will not produce these energetic neutral atoms. But we can expect if you have a hydrogen-rich early upper atmosphere or another extended atmosphere, it can easily overcome the boundary, and you have neutral particles which expand several planetary radii, and you may produce a huge cloud of energetic neutral atoms. This idea was even proposed by Eric Chassephier in 1996, when he also studied the evaporation of a Venus ocean. So what we have now is, of course, many hot Jupiters which are discovered, and there are 2 observations of 2 hot Jupiters with the Hubble Space Telescope, where they have observed the transit, but also not only in visible, but in Lyman alpha. So that means the Lyman alpha radiation from the star, in that case when the planet is in front, was absorbed. You can here see this is the out-of-transit curve of this particular planet, HD 209458b, and the thin line here is the inner in-transit curve. So you have here a velocity range, and you have here an absorption. And what happened in that case is, you see here these dashed lines, which is an example from a simulation we did with a coupled exosphere solar wind interaction model, where we can choose the obstacle, which is the magnetic field, for instance. You can see here 2 examples. So if we have a magnetic field here, and then you see that these particles are the total hydrogen particles, planetary and these energetic neutral atoms. So both of them. Here are only energetic neutral atoms which are produced due to the interaction with the stellar wind. And in that case, we moved the magnetopause somewhere further out, and you see that less energetic neutral atoms are produced. So by taking the right values, you find out the magnetic field strength you need to protect this planet. You find out, of course, the corresponding upper atmosphere parameters like temperatures and temperature, the structure of the exosphere, and you find out also the escape of neutral atoms by ionization. So now this is a very interesting point for hot Jupiters, but coming back to study this maybe on terrestrial type planets, if they really have these expanded atmospheres, what they should have in some way. So, of course, if we have an Earth around a G-type star, the contrast is too weak. It's, even if it expands several Earth radii, the atmosphere, you cannot observe it because the star is too large. So therefore, I'm coming back to M-type stars, which are, of course, much smaller stars. And we made some preliminary studies, and you can say that in that case, you have the same situation like on the hot Jupiter. There's another telescope currently developed, which is a Russian-led telescope with contributions from Germany, Switzerland, Italy, and several other Western, Eastern European countries and China, who maybe launched 2015-16. And this is a kind of, you can say, huge UV telescope, which is stationed in geostationary orbit. And in that case, we made some preliminary studies, started with it. It will be possible to observe this. And this was, sorry, I had one slide which I would like to show, but is it possible to get back? And to the end, I go fast. Okay, so what you may expect. So if you have a hydrogen-rich planet, an evaporating Venus ocean, or an early remnant of an outgassed hydrogen corona, steam atmosphere, whatever else. Okay, we may observe in such a transit really the planetary hydrogen cloud, the slow-moving, outward-flowing hydrogen atoms, and a combination of energetic neutral atoms if they could interact with the stellar wind. In case we have a nitrogen-type atmosphere, like the simulations showed by Dian Feng, for instance, then we may see no planetary hydrogen atoms because they are too slow, they are not there in that case, but we may have a production of, or we should in that case, have a production of energetic neutral atoms which form a stellar wind-induced neutral hydrogen cloud around this interaction region. So if you have if you see this, you know immediately there's a difference between, you will not see such a cloud, you will see more or less only a feature of what we have now with Hubble and the hot Jupiters. So, where we have to remove the geocorona in that case. The same for a planet with a CO2-type atmosphere. And all these expansions are different. They depend on the atmospheric species, of course. It depends also on the mass of the planet. But if we know, if we have the last slide now, if we know the size, the mass, and we could study these transits, then probably there is even a possibility to find out, let's say, to some kind of percentage, what kind of atmosphere is expanded in under these conditions. And if there is additional methods, spectroscopic methods by James Webb Space Telescope or ECHO, in that case it's maybe too far in the future, I don't know, or some other telescopes which give you hints on other atmospheric compositions. Of course, you can get a very good characterization of such issues. And we may understand really if we, in that case, if the M-star activity triggers this, then the young sun should have done it also in our solar system during another time period and so on, of course. But to finish the talk, this is some kind of activity which is ongoing in that way, and I think it may be important for understanding the evolution of Earth-type planets. Thank you.